Okay, the purpose of today's lesson is to expand upon what we learned with exponential functions to actual real life problems. Okay, so let's take a look at this do now. I have $1,000 that I'm going to invest in the bank on January 1, and it's going to earn 2% compounded annually. So I want you to complete this table. So I have $1,000. I earn 20. The balance at the end of the year is 1,020. I have 1,020. I earn 2%, so I earn $20.40. My balance is now 1,040.40. Okay, and so I just complete this problem. Obviously, these numbers are not growing significantly because I'm not dealing with a large amount of money, but hopefully you will understand the point that I'm going to get across in a couple of minutes. Okay, so at the end of 5 years, my $1,000 grew to $1,104.08. I didn't put any more money in or anything like that. Now, you learned a formula that interest equals principal times rate times time. So if I took my $1,000, that's my principal, times my 2% rate, remember you got to write it as a decimal, times 5 years, you would get $100 in interest and an $1,100 balance. Why aren't they the same? Well, the reason they are not the same is because I only earned interest on the $1,000 here. But if you see how this formula works, every time I earn interest, I'm earning interest on the interest. So in the table, you are earning interest on interest. And that's what the power of compounding does. Now, you'll see in a couple of minutes how this ties into exponential growth or decay. But just to get our definition, exponential growth or decay occurs when a quantity increases or decreases by a fixed percent over a fixed percent of its current value over successive time periods. Now, you need to know how to use these formulas that I'm going to give you in the problems and on the test that you're going to have. Okay? For growth, y, my value, is equal to a, parentheses, 1 plus r to the t, where r is greater than 0. For decay, y is equal to a times 1 minus r to the t, where r is between 0 and 1. A is the initial amount. R is your rate. Change it to a decimal. And T is your time period. R and T have to be on the same period of time to do this. So let's go through some examples. And when I do it, I'll show you what to do on the calculator. Okay. So, as with any word problem, you want to make sure that you use the strategy of underlining for what's important. Okay? But let's go back. Now we want to do the do now. I invested 1,000, 1 plus 2% at 5, and you'll see that in one very simple computation, I get what my balance was going to be. Now, on the calculator, how do you do this? It's very straightforward. You go to your calculator. It's all a calculation. So it was $1,000 times, in parentheses, because you want to make sure it does 1 plus 0.02, close the parentheses, to the power of 5, and hit enter, and it gives you your answer. Okay? Most common mistake in these types of problems is not converting the 2% to a decimal. All right, so now let's go to some other problems. Since 85, the daily cost of patient care in a community increased, underline that, 4% each year, underline that. In 95, it was $9.68 per day. So we want to write an equation for this. Well, what's my equation? Y equals 968 times 1 plus 0.04 to the t power. That's the general equation. I don't know what t is. It doesn't tell me yet. Now, I want to know what it's going to be in 2010. Well, 2010, when written correctly, is 15 years out. So now what this is asking me to do is to figure out what this number is when t is 15. And since it's money, I round to 2 decimal places to get my answer. Okay? Example number 3. Your community has 4,512 students this year. Population is growing 2.5% by year. Okay? So those are the buzzwords. Write the equation. Y equals 4512 times 1 plus 0.025 to the t power. What will it be in 3 years? Now I'm going to put 3 in for t. Always figure out what that number is, which is, and just to show you, because I want to make sure we don't make silly mistakes here. So it's 4512 parentheses 1 plus 0.0, if I remember correctly, 25, and we wanted it in 3 years. It's 4858.93. Okay? Well, that's nice. But how many people? 48. Did I say 5 or 9? 58. 4858. All right? Because that is how you round for people. Okay. Now, different question. After how many years will your population reach 5,000? Okay? Well, what is that asking you to figure out? It's asking you to figure out t now. Now, until you get to Algebra 2, where you can solve that mathematically, we're going to do it a little differently. We're going to use our calculator. So how do we use our calculator to do this? Well, what we're going to do, since we're trying to find the exponent, we're going to go into our calculator, into the y equals. I'm going to put in the equation 4512, parentheses, 1.025. But what am I going to put for my exponent? X. I don't know what X is. Remember, X is the years, Y is the population. Now I'm going to call up my table of values, and I'm going to scroll down until I see in my column for Y where I've gotten above 5,000. And you'll see at the end of year 4, I'm slightly below. So sometime during Year 5, I hit the $5,000 mark. So when did that happen? In year 5. Okay. All right. Next example. Family bought a boat in 2003, 4,000 bucks. It depreciates 7% annually. What does the word depreciate mean to the value? Hopefully you're saying it's going down. So there's my general equation. In 2008, so that's 5 years, I put in my, actually I'll convert this. So this is now 0.93, and it's 5 years, and 278782.75. Okay? If you're not getting a number less than 4,000, something should be going off, because that's telling you it's not going down in value. Okay? Then when will it be worth 2,500? You do the same thing. You look that up on your table of values, and you should see it's in year 7 or 2010. All right? The height f of x of a bouncing ball after x bounces is represented by the function f of x equals 80 times 0.5 to the x power. How many times higher is the first bounce than the fourth? Well, what this is telling you to do is find what it is after one bounce. That means put 1 in for x. And you'll see that that's 40, whatever the unit is. And then put in for x4. Again, all of this is being done on your calculator, and you'll get 5. How many times more? 8 times more. All right. So now let's do this for a science example. The half-life of a radioactive element is the amount of time it takes for 1/2 of the initial amount of the element to be left. And the equation that's used for it is the initial amount times 0.5 to a fractional exponent of time over half-life. Okay? A is the initial amount of the radioactive substance. Y is what remains after that amount of time has elapsed. Okay? They must be expressed in the same unit of time. So, the half-life of strontium, if I'm pronouncing that correct, don't get Miss Sofer on me, strontium-90 is about 29 years. So half-life, 29 years. The initial amount you have is 250 grams. How much will it be left after 100 years? So, I'm looking at my formula of initial amount, 0.5 is my given because it's half-life. Time is 100 years. And the half-life time is 29 years. Now, please be careful when you put this into your calculator, okay? Because what you're going to put in is 250 times 0.5 raised. Now, since this gives me the an exponent location here, I don't have to worry about putting it in parentheses. But if it doesn't come up with that, then you need to make sure you put it in parentheses. 100 divided by 29, and you get approximately 22.9 grams. Now, when we look at this, you'll see that it makes some sense, because if I start with 250, and you're going to see this in the table, and every 29 years, I'm going to have half of it half of whatever I started with left, that means I'm going to go through about 4 iterations or a little less. Let me show you with this table below what I'm talking about. So let's say the radioactive substance we have with a half-life of 350 years. And I want to know what happens after 1400 years. So the number of years, 350. Let's say I started with 100 units of this item. Well, how much would I have after 350 years? Half of that, or 50. Now, what do I have after 700 years? Half of that, 25. What do I have after another 350 years? Half of that, or 12.5. And then finally, after 1400 years, I should have half of that, or 6.25. Well, this is obviously not a calculation that we would want to go through in longhand form. This one's pretty easy because everything works out evenly. But just to show you how the formula works, what you would have done is 100 times 0.5, and it's 1400 divided by 350, and that would have given you the 6.25 right away. Okay? So, to summarize, what we covered today was exponential growth and decay, which is using exponential functions to figure out in real world problems future values.